everyone. Welcome to our panel on managing risks to energy systems. So I'm Morgan Edwards. I'm one of the co-chairs of the conference for those who are in the morning session, and I'll be filling in for Sarah Johnson, who's not feeling well. So we have a great lineup of talks. I'm just going to introduce folks, their names and their positions, but if you want to elaborate a little bit more on your bios at the beginning of your talk to provide some context, feel free to do that. So we'll kick it off with Sean Donegan, President and CEO of Satelytics. Then Chris Schmidt, who's a researcher here at UW-Madison at the Space Science and Engineering Center. And then finally, we'll conclude with Dean Yao, who's a solar asset manager at ConEdison Clean Energy Business. So Sean, keep it away.
Thank you, Morgan. Good morning, everybody. Great to meet you all. Super for the next 4.5 hours we're together, which is the shortened version of the presentation. I would encourage you to ask questions, please, whenever you wish. There are two aspects to what I'll show you. One will be a few very boring PowerPoint slides, and I'm not going to PowerPoint you to death. Then, you know, they say never work with animals, CEOs, or software live. We're about to do two of those things. And I hope to illustrate for you a little bit of the technology and the science behind what we do. My name is Sean Donegan. There are two things you'll notice about me. One is I'm a little nervous. The other is I speak with a funny accent. I can only possibly apologize for one of those. I'll let you guess which. We all thought July 3rd, 1776 was a better year for us. The Satelytics as a company, we're a software company. One of the main ingredients in our mixing bowl is satellite data. And we often find people get very hung up on the satellite. What does it do? What's its spatial resolution? Well, it's really just the eggs in the mixing bowl. You still need the cake, the sugar, and you just need to mix it and bake it and ice it at the end of it. And we're hopefully going to show you, or I'm going to show you some of the end of it. Satelytics today has some 40 different algorithms. We're based in Perrysburg, Ohio, or as we like to call it, the 751st most visited city in the nation. As you can tell, I probably don't take myself too seriously. This is my fourth software company I've started. I have a history of starting and managing and selling software companies. This is way and by far the most interesting that I've ever embarked on. 10 years ago, we started the company with an idea that we could solve algae blooms on Lake Erie, phosphorus, phycocyanin, and chlorophyll. Today, we measure those in parts per billion with an accuracy of plus or minus 6 parts per billion from space. Interestingly enough, we thought that was going to be our panacea, but utilities, municipalities, they have no money. Nobody wanted to spend. I still needed to make payroll. So we very quickly, our very first customer in the water space in the oil and gas arena was BP. And full disclosure, today BP is a small shareholder in Satelytics because of the work that we have done around methane and net zero in their drive to reduce emissions tremendously, not just in operations, but also looking at carbon offset and various other activities. And we'll see some of that perhaps. Our first operation with BP was looking at 25,000 bodies of water where we determined arsenic, barium, iron, manganese, and copper, and measuring those in bodies of water and on land. So everything you see with the algorithms that we have, they're all fully ground truthed. Whether we're working with a client like a BP or a Duke Energy, or whether we are physically on board Lake Erie, pulling physical samples. And the difference from a Satelytics perspective was that we not only wanted to get to identification, but also quantification. Big difference in the world of remote sensing and geospatial analytics. When I started the company, the one thing that I wanted to change dramatically was to stop using useless historical data. It means nothing to anybody whose problem is there today and how do I remedy it. So I said, I want to be able to put in the hands of our customers data within 3 to 4 hours of collecting it. That really revolutionized how we would use satellites. Satelytics today only uses satellites that are in the commercial space. Yes, we use Landsat and Sentinel, and we have used it in some of our science proofing, but we're using companies like Planet Labs, Maxar, Triple-Sat, Airbus, Satellogic. We want the highest spatial resolution possible. Now, we're agnostic to the data set, so we actually could take in data from other sources, but to drive that 3 to 4 hour turnaround, satellite is the only platform that works. And for those of you that are unaware, our goals of trying to get the data in somebody's hands for 3 to 4 years have 3 overarching goals. Number one, if you're leaking methane or you have a tree on a power line, you're losing revenue, right? You're not selling your stuff. Number two, when you have an event, remediation costs escalate dramatically and quickly into the hundreds, tens of millions of dollars. You read the press. And number three, many of our industry segments, they're often targeted by third parties, whether that's the press, the public NGOs, regulators. So anything that we can minimize keeps everything sort of in a manageable form. So that was sort of the overarching goal. We use the power of the sun shining on the Earth's surface, and our specialty, we're using a convolutional neural network, or AI, for those of you that are into technology. And we're looking at the reflective signature and the absorption value specifically for methane. We don't care about the picture. The picture is only used to show you what the science has found. The whole objective is working in the near infrared and shortwave infrared spectra. And the question was asked in the first session, what instrument would you like for Christmas? And we'd like a satellite that has midwave infrared because we think we can get to gas speciation. Our latest algorithms, number one is PFOS. And I think if you look, there's a famous Wisconsin Peshtiga where Johnson Tyco Industries settled a fairly substantial lawsuit where testicular cancer was prevalent in young males. And that was over the use of firefighting foam that gets into the water table, then mixed as slurry, put on the land, and now you've got contamination on the land. Satelytics today measures PFAS in parts per trillion from above the Earth's surface. The latest one that will be released at the end of November, we're doing the ground truthing with our client BP, is CO2. But BP started the measurement with methane many years ago. We've been working on methane for about 8 years. It was our most challenging algorithm. Normally algorithms from start to finish about 3 to 4 months. Methane took us 18. And I want to put this into perspective for you about satellite and scale. Today, you can revisit anywhere in the world 4 to 5 times a week with a satellite. By 2026, that will be every 2 minutes. And even though clouds are the challenge, if you are looking that frequently, then there will be a gap for you to penetrate the clouds. We also complement what we do with radar in some situations like the Pacific Rim, because you have dense forestry and you do have cloudy situations. Over the Bakken, North Dakota, for the last 4 years, we've been collecting data every week. To give you some idea of scale, 3,000 square kilometers collected in 11 minutes. A plane takes over 2 days, and a drone can collect roughly 100 acres every 6 hours. So satellite gives you scale. Don't need permission to look with a satellite. Nobody needs to know you're looking with a satellite. All of the advantages. Spatial resolution, a hotly debated topic in our office because we really are shocked about how much people believe that 20 and 30 meter spatial resolution is high resolution. What you're looking at here is an operational area for one of our clients. On the far right, you can see Satelytics measuring both the gas plume, methane, and also the flow rate using the shortwave infrared. For those of you familiar, there is only one satellite today that offers that. It's Maxar Technologies, made famous by the Russian-Ukraine war. You'll see their name on the TV. Images provided by Maxar Technology. The middle one is the Landsat Sentinel 20 to 30 meter and other companies that purport to be able to measure methane. And then the far left is EDF, who'd like to point the finger at everybody. But when you try and consider the mass that you're looking at on the screen from the far right to the far left in 8 data points, the data becomes pretty useless and certainly not actionable. And our contention is if you've got the best quality tool and you're working on very high quality data, the results are dramatic. We have 40 different algorithms. They all sit in the cloud. You can run them all at the same time, and literally within 3 to 4 hours, you're looking at the results, whether that's PFAS, whether that's CO2, methane, it doesn't really matter. Our objective as a company is to try and give as much value out of one set of data as possible. Our science, the root typically of our scientists is geology. We've had one biologist that's made it too, but she sadly has to sit among the rock collection of all the geologists, which seems to be everybody in geology has their own rock collection. And then we have the traditional IT with AI and traditional IT. I just want to illustrate an example, and then I'm going to show you some stuff live. What you're looking at on the screen here is a Duke Energy in the North Carolina area, where the screenshot to the left shows you, where I'm circling, the methane plume and the source of the leak. And then just to give you some idea what spatial resolution does, on the right-hand side is the source of the pinhole leak that we were measuring that methane escaping from. So even though sometimes the big bad corporations are painted that way, many of them are trying to reduce their emissions down to pinhole leaks. Duke Energy's objective is to eliminate its backlog, as well as understanding its base footprint across its entire 5-state operating area from an emissions perspective. Let's take a look at some examples, and then I'll pass back over to my colleagues. So this is Satelytics software. Once you log on, two-factor authentication, as you'd expect. On the left-hand side of the screen are some of the bigger elements you may be tackling, like vegetation management, leak detection. But the first area I wanted to show you, which I am allowed to show you, courtesy of BP, is looking at that one of those bodies of water, just to give you some idea of where we started from. So what you're looking at here is, this is Airbus, 46 centimeter by 46 centimeter spatial resolution. I know I can mention metric here because most people don't understand it in the real world. And you can see here, we're measuring arsenic every 1 foot or 1.5 feet by 1.5 feet. We've got a little feature called dual maps. It lets us look at a different timeline in the second window if we wish, or if we just keep the same timeline, we could look at a different constituent in the right-hand window. We never delete any data, just to give you some idea of the capability. And I can say, show me all the historical data you've got going back 20 years. It'll give me the range of values and the average. We are hiring, by the way, just in case anybody's thinking of a job, just graduated. We're looking for real talented people. And of course, if I wanted to, I could literally look at any particular long and lat, just pick out the actual pixel, and it will give me the parts per billion measurement with a very high degree of accuracy. And of course, because I picked it, because they're synchronized, it will pick the same long and lat on the other side. Very straightforward. You want to push all that out into Excel, just click the button, and now in Excel, you've just pushed out all of those value sets and the longitude and latitude. And of course, we have a full suite of APIs, which you'd expect. Let's get to the real turkey, though. Let's look at methane. So this is methane over the Middle East. And I'm just going to pick a particular location on a particular date to show you an example of it. And if I just zoom into this area, you'll see it's a traditional, what's called upstream or midstream oil and gas operation. These happen to be compressor stations. This is a pipeline, and you can see there are some dots. Those are sources of leaks. So the only difference with this one is that we're handcuffed for the spatial resolution of shortwave infrared to 3.7 by 3.7 meters. It's really stupid because if we're looking for methane and tree species in the same data, the trees are at 30 centimeter by 30 centimeter. The methane leaks at 3.7 by 3.7. Welcome to 1600 Pennsylvania Avenue. So we can now literally pick out any of that plume, and we measure the gas plume in ppm times m, and we see down to a low of 10 ppm times m. That's incredibly sensitive. And flow rates, we see down to 1 kilogram an hour or 8 skiff if you're in the utility space. In addition to looking at both the gas plume, we can look at the flow rate. 3 elements that we stream in as close to the location as possible: wind velocity, wind direction, and relative humidity. They affect the measurement that you have. And we're looking at the column of methane. We know that my parents are so happy that I know that cow poop is about 2.8, 2.9 ppm. You've got that same dual maps window that I showed you before. And of course, I can look at the different date, zoom into a different area, and on the screen be looking at a different set of data and show you on the screen, and also then show you the plume rate. That also applies to our friends in the urban methane area. This happens to be Duke Energy. And here you're looking at the same, but you're looking at plumes that are lower level frequent volume of data as you'd expect with delivering gas to your house. And there is the flow rate. And then the other side of the coin that is, of course, the carbon offset. These are our friends at BP, and they have a company called Finite Carbon. So this is tree speciation from above the Earth's surface. And then we overlay this with a grid. Every one of those squares is 16 meters by 16 meters. If you click on any one of them, we'll give you every tree species, its height, its health, no matter where it is. So you're looking at the other side of the equation, which is carbon offset. And that, ladies and gentlemen, is a snapshot view of Satelytics. I was teasing about the 4.5 hours, in case you didn't know.
Okay, and you could advance by pressing the next button here.
Okay. Thank you very much. My name is Chris Schmidt. I've been to Perrysburg, Ohio, and also I work here at SSEC in satellite meteorology, specifically fire detection with geostationary weather satellites. I've been doing this for about 20 years. Started out as a grad student here and got sucked into the vortex that is space science. Work with a thing called the WFABA, Wildfire Automated Biomass Burning Algorithm, and also its operational cousin. But I won't be spending a lot of time talking about that. I'm mostly going to talk about how that data is being used by some utilities. And so there we go. Okay. That's a gentle touch. So this thing that I call the WFABA was the first fire detection algorithm developed for a geostationary satellite. Brad explained what that is earlier today. But basically, those satellites are used for weather primarily and have a resolution that would, or fire from Satelytics. Old ones were 4 kilometers. This one is, the current ones are 2 kilometers. So this animation here, those pixels are generally speaking 2 kilometers. Some of them are better, but for the purposes of the fires, they're a 2 kilometer resolution. The algorithm was developed here, this one that I'm the current caretaker of, and became the baseline for what NOAA uses for its operational fire detection algorithm. And that is provided to the world through NOAA's channels. However, there are some caveats that became important and why I became involved with utilities. But basically, this thing became a NOAA operational algorithm in 2002. And in 2016, the new generation of satellites went up. And within a couple of years, interest exploded. And it exploded because the resolution got better. It went from that 4 kilometers to 2 kilometers. And people could see what we were trying to tell them for years, which is there's a lot of information here that you can make use of, even if it is pretty coarse, but it's constant. The old days, constant was 5-15 minutes. Nowadays, it's 5 minutes, 1 minute. And the flow never ceases. What I'm showing you here is those 16 different channels from this instrument, this advanced baseline imager on the current GOES. This is all the science I'll present on the algorithm itself. I could have spent 4 hours talking about it, but decided to spare you. The way this is broken up is there are 6 bands that are shortwave, quote unquote. They're all reflected sunlight. They've got the yellow dots. Dots with the bands with the red dots have emitted light from Earth. And then the one with the green dot has both. And that's also the one that's most sensitive to fires. And so as this loop progresses, and this is that fire that was near Broomfield last December, that very destructive one that ripped through town. The fire first shows up in that band with the green dot, band 7. And as it intensifies, it shows up in others. But basically, fire detection is based on what's happening in that band 7. And that's as much as we're going to say about the details of that. You can bug me later. I've also got a link to the YouTube channel on the bottom here. So one example of what that product can look like and kind of basic data fusion. Again, I'm a researcher doing satellite meteorology. I've worked with GOES. I didn't have direct work with utilities in the commercial sector. But we did do, I did do case studies. And one case study was merging the fire data with an animation from the Kincaid fire that a camera took. There's a whole series of cameras out west that watch for wildfires. They're called Alert Wildfire Network. And one of them caught the start of the Kincaid fire back in 2019. And we also had the satellite data, and we had 1 minute satellite data for that fire. And so this next slide combines those. And what you see happening here is you see a light on the hillside there, and it goes out and the fire starts. That's what's happening. The fire intensifies rapidly. On the bottom is the data from GOES, or some of the data from GOES. You've got that really sensitive fire band on your left, and next to it is another infrared band that isn't as sensitive to fires. And then there's a difference product thing difference thing that is just there to kind of highlight where the fire is in another way. And the last 2 panels are the fire product, 2 different manifestations of it. And the primary story here is, first of all, this thing blew up very fast. The animation is every few seconds, that video. The satellite data is every minute. So this is only the course of, I can't remember if it's half an hour or an hour, this whole loop. But it went from invisible, both in visible light from the camera and satellite, to showing up in the camera within a minute. And within 2 minutes, you could see it in satellite data. And within 4 minutes, the algorithm picked it up. So that's how fast it intensified. And this is a very real situation that happens out west quite a bit. This particular case was of interest to PG&E because they got blamed for it. So I can't say whether or not it was determined that they were responsible. I frankly don't know. But this kind of data was important to them, seeing this kind of thing, which leads into, this is just another example of showing that 1 minute step between when the fire wasn't there and when it was. But this segues into why the utilities care, or why these utilities out west care. It actually started well before the last few years. The previous generation of the algorithm, previous generation satellites had grabbed the interest of our friends from South Africa. And one gentleman in particular, Phil Frost, who developed a thing called APHIS, the Advanced Fire Information System. And their job was to alert the interested users, primarily utilities in South Africa, about threats to their power lines. And he was really interested in satellite data because they had nothing. They didn't have the kind of coverage that you get in the US of people, and not even that much in satellites. They had the European weather satellites and not really a great way to access the data. So for a long time, we provided them with fire data. And they presented this idea here in the US a few times, but it didn't really take off again until about 2018, after things really got bad in California. So that's when PG&E approached us and they said, hey, we want to get at some fire data. And we talked through the options. We're not an operational shop. SSEC is a research center. They really should, quote unquote, get it from NOAA. But NOAA didn't have a good pathway for this data. It really wasn't available directly to the public at all at that point. We could kind of mirror it to them, but there'd be like a 15-minute delay. Not good. That's not what they wanted. Also, NOAA wasn't processing the 1 minute data. They were processing data at 5 minutes, 10 minutes. So this stuff would be 10, 15, 20 minutes old by the time PG&E would get it in best case. What we could offer them was the opportunity to process just what they wanted, just California, do it for everything goes sent down, which means there would often be 1 minute data, and times even 30-second. I won't get into the details on why that is, but sometimes even that fast. And that would give them really low latency. And they'll initially promise like a 2-minute latency. It turns out to be 20 seconds. So within the time the data comes down and they get it, it's about 20 seconds. And they were very happy with that. As time progressed, a couple other companies also approached us to do the same thing. Actually, there's been others too, but we've got arrangements worked out with San Diego Gas and Electric to do the same thing for them, and a company named Fireball, who is also providing downstream products to other users, including other utilities. You've heard it mentioned before, even in the previous talk, that part of the issue here is that connection between this kind of raw data and useful intelligence. And so when it comes to fire work, I'm sorry, I keep popping on the mic. There is a large amount of disparate sources of information that they can make use of, but it's got to be brought together somehow. There's this effort to develop these integrated intelligence systems to do that, to merge these sources. You've got the satellite data where the great advantage is persistence and just general availability. And for fire uses, at least, it can be pretty good for finding things early. We can see pretty small fires. We can see house fires sometimes. And I said, this is a 2-kilometer wide pixel. At the equator up here, it's more like 3. A decent sized house fire, like a 1,200 square foot house, we can see that, especially in the winter when it's cold. So there's a lot of sensitivity there despite the coarse resolution, or relatively coarse resolution. These groups also have access to various forms of aircraft data, but that's only available in certain cases. They have ground-based sensors. Some of them are static, like those cameras. Cameras rotate though. They have a rotation schedule for a lot of them, which means they're not always pointed in the same place. There might be a 5-minute gap between looks. And there's other things too. They've got other people on the ground, but there's this combination of resources that are available and that can be deployed, but satellites are the only ones always there and always available 24/7. So what does PG&E do with this stuff? They developed their own system called the Fire Detection and Alert System. They take in our satellite data and they merge it with some other information. Now we set up this whole thing with redundant servers to provide them with some security that they're actually getting this stuff. And they take in our data, which includes location and properties. And they also estimate the satellite footprints, which is relevant, and I'll show you that in a second. And they put it into a GIS system. And it also brings in data from VIIRS and MODIS, but the delays on that, those are polar orbiting satellites, which have higher resolution, but the delays are, in the best case, maybe an hour, usually more than that, for when they actually see that data. So that's not exactly a real-time thing for them. That's more of a monitoring things that are higher resolution. They also have sources of data with fire perimeters from a thing called FireGuard, which is a secret thing run by the National Guard. We don't know exactly what they're using precisely. They do push out alerts. Those alerts often lag behind the ones from the satellites, probably because they are deliberately lagging them, but I don't exactly know. So they have these internal and external components to this system, but for the public facing side, there is a interface that shows things like this. And so this is this fire pixels from 2 different satellites. One is the GOES 16, which are slanted to the upper left. GOES 17 is slanted to the upper right. And in this case, they're both showing the same fire complex. They don't overlap perfectly. There's various reasons for that, including the terrain. These things were not terrain corrected at this time. But basically, this gives PG&E a lot of confidence. Yeah, there's something happening here for sure. And they internally deal with that. They have an alerting system built off of that, where when the system picks up a situation like that, it pushes out an alert. And there's an example notification text on the bottom for a certain case. In this case, they could verify it with the camera. They saw the smoke plume, algorithm picked up the fire, and and their system can show where the cameras are pointed and that kind of thing. Other cases, You may not get camera notification right away, or maybe hard to see. This is a pretty small fire. You know, this is slash burning going on or something like that, but it's small and may not be noticed right away. Still got picked up by the satellite, still could verify it with the cameras, and there you go. They also can track things over time. And just another view of that system. This is from the public face of it. And here's a large incident case, again, where they can track the entire incident. They have the maps from both satellites, and see they don't overlap properly. There's kind of that separation. That's something we're fixing right now to make sure that doesn't happen anymore, but they've learned to adapt to that for now. There is false positives. This is a problem with these algorithms in general. This one in particular, not getting into details again why it happens, but in this case, it's sunlight reflecting off the surface, large area of these low-grade detections, only visible from one satellite. They know we got to throw these out. That's just sunlight that hasn't been screened out other ways yet. San Diego Gas and Electric has a similar thing. Although their system is not as refined, they initially just brought them in for internal monitoring. They just got the raw files, watched them themselves. Eventually, they wanted to move to an alerting system, and they partnered with Wi-Fi and San Diego Supercomputing Center to generate simple alerts like this one here. That's the email that you get. It's actually the most recent one. They have a small area. They're basically just south of LA, Southern California, south of LA. And there haven't been a lot of fires there lately. So that's the most recent one. And it just generates this and links to a map that has, again, the cameras. Cameras are a critical piece of this, and location of the fire. And if there was a fire there, there'd be more information about the fire itself. Wi-Fi is this great group that's doing a lot of work with hazards out in California, including very high level of modeling associated with these things. So there's going to be a lot more coming from them in the future. Fireball is yet another similar entity. The one difference with Fireball is they added in automated detection of smoke using AI with that camera data. And so they scan the camera data looking for smoke plumes. And it's into this nice integrated mapping system where you get an incident, you can see views from the cameras, you can see the satellite data when you query it, and use it that way. And that's it. This is just a link of images from the Caldor fire, the algorithm again, just showing it works. And that particular image happens to be Reno, Nevada, about a year ago. I was there one day. It was kind of nice weather, and all of a sudden the smoke from Caldor came in. It smelled like a campfire and looked like that. So that's it.
Okay, you go. You can advance with this one.
All right, good morning, guys. Can y'all hear me okay? Yes, great. Yeah, it's great to be here. My name is Dean. I'm gonna talk about managing risk to energy systems. So let's get started. All right, so I'm gonna talk very briefly about me. So I'm actually an EAP alum. I graduated in 2019. I was also doing my MBA program here at the school. So I'm like a MBA/EAP person. I think there might be like 5 of us in the whole history of EAP, but hopefully there will be more. And before that, I was a plant engineer. I was working at a combined cycle plant that burns natural gas out in Oregon. And since I graduated from EAP, I've been working in asset management for ConEd, clean energy business. And I manage a few portfolios of utility scale and behind the meter solar assets. Okay, so spoiler alert, I don't have any fancy discussion about satellite data for this. So this is more of like on the ground view of what individual asset operators do to maintain system reliability. I know we care about that a lot. You got to keep the power on in the middle of a storm. And there are thousands of power plants out there, and what is everybody doing to achieve that goal, right? So I'm going to have like a couple take on this, since I have some experience in both fossil and renewables. So I'm going to start on the fossil side. A combined cycle plant is basically a gas turbine coupled up with steam turbine, and these are pretty basic mechanical systems, but they're still relatively complex and with lots of moving parts and lots of things that can break. So, if you want to maintain system reliability, especially, during times of a cold snap or hot weather, the key is basically do your preventive maintenance. You have a crew go in there every year, basically do your borescope, do the combustion inspection, looking at where the flame comes out, and the hot gas goes into the turbine. Make sure you don't have any cracks, don't have any things on your blades, no corrosions. So when you call this, when you require the system to work, it's going to work. It's not gonna, you don't press a button and something explodes. So that is really the main thing. And I remember every year, I would go in an outage, and then there will be technicians crawling all over the turbine doing inspections. I would also be crawling all over the steam generator, basically looking for signs of corrosion, looking for signs of crack, and then crawl around the steam drum with a flashlight and a little Sharpie, basically circling all the cracks out there. And then I go and tell the water side, fix this crack, fix this crack, fix this crack. So that's what I did during the annual outages. And then another thing that is important, because my plant is up in the northern realms where it's really, really cold. So winterization is key, and it depends on how your plant operates. It really could trip you up. My plant was merchant, so it basically runs when the power market is good. And what that means is that sometimes, well, by sometimes I mean all the time, we basically shut down at night, even if it's cold. And when you shut the thing down for 10 to 12 hours in minus 20-degree weather, well, maybe not minus 20 degree, 0-degree weather, things tend to freeze up. And when you try to go start the plant out in the morning, things break and your system is not going to work, and the grid is going to be short those 400 megawatt or however size your plant is rated for. And in the hot weather, it's not so much. So we mostly concern in the winter. And in some of the summer, some of the more southern regions where it's usually not much of an issue, like Texas, maybe folks are not so diligent on putting installations on things. And when you have a very unexpected cold snap, like what happened a couple of years ago, you get a bad situation. Okay, so how about on solar assets? Solar assets are a lot more simpler mechanically. It's it's basically a bunch of solar panels string up like Christmas tree lights. And then everything kind of goes into a combiner box, and then multiple combiner box goes into an inverter, and then it goes through a transformer, goes to the grid. So there is not much, or there's not as many things that you have to do, but we still have to make sure the system is operating right. So one of the things we do is that we do a drone inspection. We try to do it every quarter. So I just threw up a picture. So on the left is what the human eyes can see, but on the right is what the drone sees. So so it's just like a drone with 4 little rotors. And on the belly of it, there's an IR camera that basically looks at all the solar panels and flags problems. See, I think I have some. Okay, I have like a real quick example. I just pulled some pictures from one of the reports that I have on file. So this is actually one of the plants I manage. This one is in Pennsylvania. It's 10 megawatt AC. So it's capacity is not so big, but it still takes up a lot of land area. It's one of the drawbacks for solar systems. And so a drone flight does a flyover, and then it does the scan, and then it produces a report that looks something like that. It's pretty self-explanatory, I think. So on the upper right-hand side, that's the highlighted area is what you're looking at, and on each panel, the camera with the algorithm will be able to look at what's wrong with the panel, and it basically flags them. Those crazy string of numbers with brackets, it's actually like a location code. So the technicians on the ground will know which panel they need to go swap out. And then, if you look at the legends, it tells you like what the problem is. And another part of the report, it's kind of like a zoom in view. So I think on the upper left-hand side, you got a couple of hotspots. And on the right-hand side, there's like some kind of open circuit. And I got a few more examples here. The top one is like an open string, so there's some wiring problem. Like that whole string is basically offline, and then a few more hotspots here and there. So that basically indicates there's some issue with that cell. So something's shorted out. Or maybe like connection is loose, or wires messed up somehow. So you can kind of go in and look at what's wrong, and then have your guys replace it. They usually just go in, swap panels out. It's pretty quick and simple. The main thing is to be able to identify problems at a relatively large scale. So I'm going to go back to those slides. So this is like a relatively small system, and this site is like 50 acres. We have sites out west, like in California, that are hundreds of acres. So imagine walking each row on foot, or on a little cart. That's kind of infeasible. That's why we use drones to kind of fly these things. And what else? Maybe one day satellite will come into play, but we'll see how that goes. And so one of the things we actually do at the solar site, it's actually one of the biggest expense, believe it or not, is to cut the grass. So these are basically solar panels propped up on a field of grass, and then grass likes to grow, and then they like to get really tall if you don't cut them. So it's not so tall, it's not so high off the ground if you look at the bottom of the panel. So one of the problems is that when the grass grows tall enough, it kind of covers the front half of an array. So that reduces your output. And another potential problem, this hasn't happened at my company as far as I know, and I think it's pretty rare. And it's more of a concern out west, is that grass gets dry and solar panels are actually pretty hot when they operate. So on a warm day, a panel can get to into like the mid-30 degrees, mid-30s Celsius. And if a panel has an issue like hotspot or something, it can get a lot hotter than that. So, and California is pretty notorious for having dry grass. So if you neglect the landscaping, you know, there could pose a fire risk that you know, it's one of the things that kind of keeps the California guys at night. Is that, you know, what happened if a hotspot kind of ignites some dry grass and then it goes to burn down half the state. So that's one of the things that we worry. Okay. And so switching gear a little bit, we also work with regional transmission operators, and as a combined cycle facility, we usually have control signal directly goes from our balancing authority. So after we start the plant up, we could hand over, you know, to those guys. They can ramp us up, ramp us down based on what the supply and demand situation is, or they can just call us to say, you know, you need to go down 20 megawatt or something like that. For our solar assets, the ones I have, they're all kind of old. They're like 10, 15 years old. So, you know, so they have nothing. They're just, you know, they are, you know, intermittent resources, not dispatchable, and they will just do whatever it does, depends on what the sun's doing. One of my newer assets actually does have some limited control capability. So the RTO can send a signal to curtail. And so, you know, if there's too much power, they can decide to shut my site down. But they can only curtail, they cannot increase production. So that's what that is. And so lastly, just want to talk about the incentive to maximize availability or reliability. Obviously, we as a merchant plant, we get paid. So, you know, at times of peak demand, we get the most money. So that's why we want to always maintain system availability and be able to start up when we're called on. So, you know, we can make money. That's what happened. That's what's important at the end of the day. And some of the PPA facilities are, you know, we basically get a fixed price per megawatt hours of production, and so that's great. And we also usually have a availability guarantee built into our contract. So, you know, every year we need to be able to maintain for 85% of the theoretical power or something like that. And, you know, you need to maintain like 90% availability or something along that line. So those are our incentive to, you know, keep our system reliable and keep availability high. And my last point, I just decided to throw in there last minute, is that I also have one little battery system out in Massachusetts, and we sell CPEC, which stands for Clean Peak Energy Credit. So it's an ISO New England thing, and what it does is that during peak hours every month, it rewards us for being able to dispatch power. And there is like it's like a $45 per CPEC base price, and there's like a bunch of multipliers that stacks onto it, depends on the condition. So that can, you know, go up to, you know, $100, $200 or more per megawatt hours that we dispatch during the period of peak demand. So, you know, that's a nice little adder for that asset. So yeah, and that's really all I have for now. Thanks for listening to my rambling. Hopefully that's informative. And that's all my time.
All right, so I'll invite our panelists up to the table here and take the first question.
Hi, I'm Zach. I'm a PhD student. I have a question about using satellite data for long-term risk mitigation. Like, are you able to use like the data you have collected for identifying like immediate short-term risk, like in the scale of a day or a few hours, to like plan scenarios for reducing risk in the long term? Like, for example, identifying being able to identify like the ways wildfires spread to prevent large fires in the future.
Well, let me take a stab at it and then see. So we never ever delete any data. So the objective is to do just what you said. If you look at a lot of natural gas pipelines, going back in time, the history of the United States, a lot of the pipe below ground was steel. And that's aging. You know, look at our oil and gas infrastructure, is probably 100 years old. It's a remarkable, we don't have more. So we want to identify the leaks very early on. So even before they come above the surface, things like produced water, liquid hydrocarbon leaks, we're spotting those. Our canary down the mine is often vegetation. Vegetation is incredibly sensitive and gives off a chlorosis signature, so we know where they are. But it is in that vein of capital replacement. And then with wildfires, the work that we do with people like PG&E and Southern California Gas is we want to get out and understand a tree species, its certain height, its soil moisture content, because we'll pro-harvest that before it becomes a wildfire threat. Same with the ash borer beetle. So if you're in the upstate New York, Poughkeepsie area, Central Hudson Gas Electric, largest ash tree population in the country, that ash borer beetle gets at the middle, falls on the lines. And then once you have a slip or a slide, we've got removal of vegetation, we're looking at burn scar risk for potential wildfire. So yeah, it's used, I mean, clearly we want to eliminate any event, but any data, you know, I know I was flippant and saying stop looking at the history, but any data becomes a predictor of the future, particularly land movement, because slips and slides, if you look at West Virginia, 481 in the territory that we look after on average a year, typically after snow melt and spring rains, where you've got the highest volatility of land movement, which, you know, has its own. I'm sure he's got a better answer.
No, I don't actually. Is this the mic you want us to use, by the way?
Oh, sure. Is it on?
I don't know.
Okay.
I don't really have much to add because, again, I'm more in the real-time fire detection. If anything with wildfires, though, what we've been seeing is this massive increase over time due to climate change and also due to expansion of humans into what we call the wildland urban interface, the WUI. There's more opportunities to start them and more opportunities to cause a lot of damage. So predictive value of historical fire data goes not so great in the US, at least. You may, you know, but it's data fusion is what it comes down to. And using it with other sources if we want to try to figure things out like that.
Are you a wealthy student, sir? Can I ask that question?
No.
Because when the professors, some of our scientists say when they join us, they say in geology, and just before the Ukraine-Russian war, I can tell you this is a fact, arsenic is a predictor of where gold is. So the professor plays with the minds of the university students and have them all looking for arsenic concentrations. But just before, you know, we pulled out of the whole Russian thing, we had a number of Russian companies looking for concentrations of arsenic. So looking at historical records, because that would give you a high indication of gold and mining. The same with rare earth elements. You hear about rare earth elements. It's certainly an area that we are pervasive in, but the debris that comes out of harvesting earth elements is more costly than it is to harvest them, you know, to get rid of it. Anyway. So you're not a rich student. Okay, got it. I can show you how to look for the arsenic if you want.
Hi, my name is Rob Sternsian. I'm the CEO of a startup company called Scenario, and we do statistical climate simulations for energy systems. My question is for Dean. I'm curious about how you think about solar production risks due to snow, given that you manage solar plants in the Northeast. Could you do maintenance around snow, just let it sit there and melt off, and also think about it kind of long-term snow risks?
Yeah, we let it sit there and melt off. Yeah, like, you know, solar panels are pretty warm. So, you know, unless for some reason you have like a freak snowstorm, you know, you got 2 feet of snow in 2 hours, something insane like that. It's usually okay. Solar panels are pretty tall and they're pretty large, and then most of them are kind of at an angle. And as long as they're not like totally covered, like the little part is going to work and it's going to warm the whole thing up. And so yeah, the snow basically melts away. So most of the time, that is not a huge issue. There is some instances in like upstate New York, like really upstate, like close to Canada, where we do have a lot of snow, then that kind of becomes a problem. So yeah, that's my answer.
I'm Tracy Holloway from the University of Wisconsin-Madison, and I really appreciate all the presentations. And I guess my question is a little more abstract, which is thinking about the role of proprietary information and public information to different decision makers, because I think we've heard from Satelytics as, you know, a company that's providing other companies with satellite-based data, and then we've heard from Chris using government-funded, large-scale data sources to inform wildfire risk. And then Dean talking about, you know, using drones as a very, you know, in-house way to get information. And I think, you know, we're all talking about different ways of sensing for energy systems, but some of the data are public and some are not. And some of the stakeholders, like states and federal agencies, are public and some are not. And how do we like leverage those resources and tools in a way that makes sense?
I can start with that. This has been an issue that I've had to consider working with the utilities, and my basic angle on it has become, I don't assume that I'll have access to everything, and that's going to be why there's always going to be variation in the ecosystem, if you will. I showed 3 different systems that basically do the same thing, but they have subtle differences in what they ingest and what they have access to. Some of it's proprietary. That was an agreement. We had to make that clear in all the agreements too. Is like this stuff belongs. There are certain things that belong to everyone, certain things that belong to the UW. You know, and what belongs to you is just the data. You know, any changes I make are not yours; they're ours. But it still works. We can still make it work. Probably the only place where it's been an issue really is with the top secret side. And we don't know what they're doing. They're an important component in the chain for providing this fire information. And that it doesn't cause problems per se, but it causes confusion, especially when trying to look ahead toward designing things that are, say, specific for fire detection, satellite specific fire detection. I've been involved in a group trying to do that for a geostationary one. You know, it would be great to know what the DoD does. We can't find that out. None of the commercial entities really try to do that specific thing, so we can't leverage any of that proprietary. Anything to add to that?
Yeah, there's a high level of distrust for the private sector with the utilities, with the regulators and governments, whether good or bad or indifferent, it exists. And maybe for good reason. I'm not here to sit in judgment of that. I just run a small little business in Perrysburg. But we serve 7 market segments, one of which is oil and gas, traditional oil and gas, and mentioned BP. Many of its peers are fiercely private. They want to do the right thing, and they are doing the right thing. They're just not going to make a big song and dance about it. They'll go quietly along their way. I think there's a parallel to what you said, though, Tracy. Duke Energy, as a company, committed to eliminate and reduce greatly its methane reductions. It's the largest utility, in case anybody wants to know, in the United States. I think they've taken a pretty unique step. So they've dragged PHMSA and the EPA kicking and screaming to the altar of following them in what they're doing with new technologies. So, and they're doing it for 2 reasons. Selfishly, I'm sure they want to influence the final regulation, but it's a smart way to show the government agencies and others that are looking over their shoulder the efforts and the extent and technology that can be applied. And I go back to what I said at the beginning. Most government agencies think 30-meter by 30-meter spatial resolution is a revelation. And when you look at some of the stuff I've shown you, It's far from it. You couldn't pick out a pinhole leak using that course of data. So, you know, no horse in this race, but I will tell you, I've yet to meet an executive in the segments that we serve that doesn't want to do the right thing for all manner of reasons, not least of which is to have their face plastered across, you know, social media or some publication. It's a gap though.
30 meters is a revelation.
Okay.
So the guy who just took.
My mother said if I was a revelation, I'm still alive, but that's a whole different topic.
So I want to go back to something that was mentioned in the first presentation having to do with costs incurred by leaks. And that I don't know the numbers for methane, but, and this is kind of coming off the question of public access to information. But with the Line 3 oil leak currently in Minnesota, it's being discovered that they bake into the cost to the ratepayers roughly 10% leakage of oil. Do you know what the number would be for methane? Because in a utility model, if they're just baking in the cost of a leaking project or a leaking product to the ratepayers, then the cost to the company is really the PR damage and that you have a leak, but not that you're just leaking resources into the environment.
Yeah. Again, I'm going to address your question, Miss, but I want to go back to what I said about being fiercely private. That is very much a utility by utility, and I haven't studied whatever leak you talked about in Minnesota, but I will tell you the big leaks are easy to pick out because the SCADA systems go off, the alarm bell goes off very quickly. What's the silent killer is the drip, drip, drip that can go unabated. You can look in the public records, there are many examples of this. So that's why, you know, clearly as a business, I wanted to set out to prevent that. When it comes back to rate, if I may, there's some pretty strict, tough rules around just simply passing it on to the consumer. I live this day in and day out. It's not as easy as it's sort of laid out to be. And again, I'm not in the utilities, I'm just a simple software company. What I find astonishing is that, and they'll remain nameless, I can tell somebody for 4 years, we should be monitoring this area. And it takes an event which costs the entity a lot more money to clean up for them to come to the altar and say, let's get this done. That to me defies logic. If we do our job well, you never get those events. The trouble is, in the commercial world, they say, financially justify your being. And I say, well, if I'm not sure how I could do that because I'm going to, unless you can tell me what your event is and the cost of it, I can't really put it into perspective. Does that sort of make sense? So it's not an easy question to answer. It's a question I'm asked all the time, but people are fiercely private. And, you know, if I start talking about some of the stuff that I would know, they'd shoot me. And, you know, I still have to make payroll this week. Next week, it's fine. This week, I have to make payroll.
Thank you. Hi, my name is Joe Rhodes. I'm a PhD student in electrical engineering. I work in restoration planning of power system. First, I guess, sort of one comment, I have a friend who's in the National Guard, was recommended to work with this satellite data with military and can't get him to say anything about it. Asked lots of questions last month.
Right.
Such small amounts that you can say. My question is about restoration planning and the fact that it's very hard to get any solid information to even start the planning process. The question I have is, what would it take for help with a lot of satellite data to be able to save the network? Hurricane comes through Florida, how easy is it to actually say these are the outer parts of the power system and be able to start restoration planning?
I don't know if I have a good answer for that. So usually what power utility does is that they have some kind of emergency response planning procedures in place. So if they basically watch the weather, if they see something bad coming, they start getting people lined up, start flying in a lot of extra crews and materials to the areas that I think is going to get affected. And then when the bad thing comes down, then they go out and
and start fixing things. I don't know. Yeah, I don't think that they have any. I don't think they are leveraging anything like satellite data at this point yet. But yeah, who knows? Maybe one day they can. They will be able to predict a little better, like which areas will be hit. Yeah, but right now it's you can get a pretty good idea like which way the storm is heading, and you can kind of guess how bad it's going to be. Like
So literally within, as soon as the clouds clear from a storm, we're doing this right now over Florida, offering it for free to show. There are two things that two or three things that people are particularly interested in. What's called land classification. How has the land changed? So where is the water where there wasn't before? Obviously structural, you want to know what poles are down and what has been taken out. And then you also want, you want effectively a good picture of what's called change detection. So, what was the before and after picture? Here's the challenge. Don't try and get me to put the genie back in the bottle, because the data may not exist over the area previous to the storm, and then suddenly think I can work miracles after the storm. High resolution data is not just available. You normally have to task those satellites pointing over your infrastructure. So you have to be aware and get out ahead of it. The department that's normally involved in that is disaster recovery, and most utilities will have a group that's specifically designed to do what you've asked.
I feel like it's important to add, the reason I can't answer that question is precisely what he's been pointing out is resolution. The geostationary weather satellites are 36,000 kilometers up. Satellites he works with 400 kilometers, maybe less. And so they can achieve much better resolution. For GEO to get the kind of resolution to do that kind of work, you would need an optical system that is absolutely gigantic and beyond our capability to actually fund and launch.
I think this will be our last question. Two more questions. Okay, we'll gather them both and then we'll let the panel answer.
Hi, my name is Andrea Lang. I'm faculty at the University of Albany in New York. And so my area of expertise is subseasonal prediction. So on the time scale of weeks to a season. And much of what we've been talking about today is thinking about things in real time, finding, detecting disasters essentially after they've happened. But do you all communicate the potential risks to sort of focus mitigation or maintenance to prevent some of these disasters? And if so, how do you integrate that into sort of the decision-making time scale or a series of events?
One more question, then we'll do answers to both. Where is that student question?
Good afternoon. My name is Raul. I'm an undergrad, and I have the pleasure of being a student of Professor Howells. I just want to say thank you guys and to the organizers for taking time out of y'all's day for this conference. But I specifically just want to ask, to be completely honest, I don't understand much about the topics that y'all discussed, but I just want to ask from y'all's profession's standpoint, how are y'all able to move laterally, and how flexible has y'all's work been in being able to look in different industries or different professions?
Well, I'll try to answer from the sequence and ask around, I guess. As far as predicting on more climate scale, I guess would be accurate to say a longer scale. I don't have a lot of role with that directly. I've worked with occasionally people who've done trying to analyze the satellite data for fire detection, say, okay, this is where fires have happened. That means there is an increased risk of landslides, or problems when there's a lot of rain, or low risk of fires with the immediate future. But that's been the extent my work has been. They might have different answers. As far as spreading laterally, if you will, the work, it took a while for it to happen. I've been going to meetings and trying to get my face over. I've basically been the only guy for a long time doing this. So I would go to meetings that were outside of our normal realm, trying to drum up interest in the fire products and also those products in general. And it really only took off when the interest got high enough on the commercial side and the financial risks became high enough that they had to start looking for people to pay to do this work. That's when it changed for me. These guys may have different answers.
Yeah, I'm just in this one industry, so I'm pretty happy.
We're hiring, sir. Take your hat off. Let's see what you look like. So, Ms., the question about long-term, we're a piece of a jigsaw puzzle. Whether the data is relevant for the long term, it clearly, history often sadly does repeat itself, particularly when it comes to slips and slides and disasters like that. I mean, there's something you just cannot change about the topography of West Virginia, where, you know, snow melt and spring rains are going to be snow melt and spring rains. So we become an integral piece of a jigsaw puzzle, which then becomes a bigger part of a decision-making process to try and get out ahead of them. To your question, sir, about laterally, you should be on the stage. That was a good question. We, as a company, when we started off looking at Lake Erie, and we thought harmful algae blooms were going to be our lives, because Toledo shut down its water supply in 2014 due to harmful algae blooms. But we had to laterally move because it wasn't paying the bills. And, you know, my bank manager wrote to me and said, "Dear Mr. Donegan, you bank with us, we don't bank with you." And then, but as you get into discussions, I mentioned about PFAS and the lateral move. I saw a woman with the DOD talking about this firefighting foam. I called my chief scientist and said, "Look, we got to start some work on this." 3 years later, BP asked us and said, "I know it's a long shot. What do you know about PFAS and firefighting foam?" And that led to the development of that algorithm. Here's one that's very interesting. We do an awful lot of work in the Permian Basin, which is the largest oil and gas field in the United States, Texas, New Mexico, that sort of area. But and this ties back to University of Texas Lands, it's called. They own 3 million acres, some of which they lease to the oil and gas companies. The other millions of acres they lease to ranchers for cattle grazing, dairy farms, which of course you know well in Madison, and livestock. And there's an invasive species from China called cheat grass. Bayer, which you may have taken an aspirin from, the West German pharmaceutical company, sells products that restores the native grasses. So they want us to monitor where is this invasive species, and as they apply that restoration juice, how effective has it been, and then measure the production of the dairy and the cattle farm. So there's a real lateral move that we would have never dreamed of in a million years.
That explains why there's a Bayer facility on US 14 just east of Janesville. I've always wondered about
Yeah. There we go.
All right, well, it's now time for lunch. This has been a fascinating panel, and I think the issue of risks really is an undercurrent for all of the panels that we'll be having, risks to energy systems. So let's thank our panelists again, and we can follow up with more questions.